So today we are going to discuss the main Galois theory. Before going into the theorem, I want to refresh one definition that we already did it earlier, that is fixed field. So the definition is like this: if E is an extension of F and sigma I belongs to some index set, be isomorphism on E, leaving F fixed, then the collection E sigma I belongs to I, is equal to A in all elements from E, such that it is not changed by any of the isomorphisms in the collection. Then this is a subfield of E and is called the fixed field of the collection of isomorphisms. We are going to use this in the theorem. So the way I'm going to state the theorem is like this. I'm going to start with an example, and when we progress with the example, we are going to state the theorem here. So actually we are going to start this theorem from the previous result. So we have a finite normal extension of a field. So we'll take F is equal to Q and K is equal to Q of root 2 comma root 3. So this is a finite normal extension of F. This is finite because the index is 2. It is normal extension because it is separable, and this is a splitting field. So we'll write it here. Let K be a finite normal extension of F. Then what we are interested in is all the extensions of F within F and K. Extension of F, but again subfield of K. So what is the index of this? The index of K over F is equal to 4 because the vector space is generated by the basis 1 comma root 2 comma root 3 comma root 6. So if you need to find out an extension of F in between F and K, that has to be either 1 or 2 or 4. If it is 1, then it is F. If it is 4, then it is K. So the non-trivial extension of F will be of index 2 over F. And that is because k over f is equal to k over e times k over, f over e over f. So this is 4. So the product has to be 4. So that should be 1 into 4 or 2 into 2. That's what I'm saying. So if it's a non-trivial one, it has to be 2. So what are the possible extensions of non-trivial extensions of f? The non-trivial extensions of f are, we'll write it as e root 2 is equal to q of root 2, e root 3 is equal to q of root 3, e root 6 is equal to q of root 6. These are the only ones. Okay? So the extension diagram will be like this. K e of root 2, e root 2, e root 3, e root 6, and there is an f here. So this is going to be our diagram. So we are going to write here, let E be an extension of f where f is a subfield of E, this is a subfield of K. This E could be any of this. Now we are interested in the automorphisms on K fixing f, that is g of K over f. This is a group of automorphisms that leaves f fixed. The elements of this group is determined by 1, root 2, root 3 and root 6. So the automorphisms are, there are only 4 automorphisms. The automorphisms are, the first one is I, which is actually 1 goes to 1. See, when you define the automorphism, this should map to its conjugate, this also should map to its conjugate, this also should map to a conjugate, and this also should map to a conjugate. So one's conjugate is always 1, nothing else. Then root 2 should go to root 2, root 3 goes to root 3, and root 6 goes to root 6. That is one of them. That is the identity map. Identity map is always an automorphism. Another automorphism is sigma, I write it as sigma root 2, which is 1 to 1, always like that, because then only you can leave f fixed. Then root 2 is unchanged, but root 3 and root 6 are changed. Root 3 goes to minus root 3, root 6 goes to minus root 3. And root 3, sigma root 3, 1 goes to 1, root 2 goes to minus root 2, root 3 is unchanged, and so root 6 is going to be changed. and root 6, 1 goes to 1, then root 2 is changed to minus root 2, root 3 is changed to minus root 3, and root 6 goes to root 6. So these are the only 4 elements in this group. And we already showed that all the collection of all the automorphism under composition makes a group, and it's called Galois group here. So we'll write it like this. So let G of K over F be the Galois group of automorphisms on K leaving F fixed. Now let us compute the subgroups of this. The subgroups of these are, of course, the first one is, see the order of this group is 4. So the subgroups have to be either 1 or 2 or 4. So the subgroups are just the I, and you can have I and sigma root 2. You need to verify this because this is going to be a subgroup of this. Sigma root 2 square will become I. And the other one is I sigma root 3, I sigma root 6, and the whole of the Galois group of K over F, that is root 6, root 2, sigma root 3, sigma root 6. So these are the subgroups. So we will write it like this. So the subgroup is we start like this. I, then this is order 1, then we will write the order 2 here, that is I sigma root 2, then I sigma root 3, then I sigma root 6. Then you have I sigma root 2, comma sigma root 3, comma sigma root 6. Here also you have 1, 2, 3, 4, 5. 5 elements. So here F is a subfield of E root 6. It's a subfield of E root 3. It's a subfield of E root 2. And E root 2 is a subfield of this. And arrow goes like this. Here the arrow goes down. This is a subgroup of this. It's a subgroup of this. This is a subgroup of this. And these are all subgroup of the whole, the complete collection of automorphism on K leaving F fixed. Now, what is this? See, when you compute G of K over K, what does this mean? This is the group of all automorphisms on K leaving K fixed. So there is only one, that is the identity map. There is no other automorphism will leave k fixed among these. So this you can write it as g of k over k. This one, g of k over e root 2, is the collection of all automorphisms on k leaving e root 2 fixed. This is the only one which fixes root 2. So that will be I, definitely I will be one of them. Then this will be sigma root 2. So this will be g of k over e root 2. Similarly, this will be g of k over e root 3. This is g of k over e root 6. And finally, this will be the whole collection of all automorphism, which is g of k over f. So we will write it like this. This is equal to g of k over k. This is g of k over e root 3. This is g of k over e root 3. This is e root 2, this is e root 3, and this is g of k over e root 6. And this will be g of k over f. Now, my next step is, see, now you have two collections. This is the collection of extensions of f, and the collection is f can be considered an extension of f, then e root 2, then e root 3, then e root 6, and then the k itself. This is the collection of subgroups of g of k over f. And what are the subgroups here? G k over k, k over e root 2, k over e root 3, k over e root 6, and k over f. Here also you have 1, 2, 3, 4, 5. We need to define a map from here, and that is called we normally denoted by lambda. From the collection of extension of f to the collection of subgroups of f. We can always say that, by the naming convention, f can go to g of f, e2 can go, e root 2 can go to this, k over e root 2, things like that. But besides that, there is a relation between these two. See, if you take k over g of k over e root 2. This means the fixed field of the collection of automorphisms in this subgroup over k. So that is equal to elements from K such that for sigma belongs to G over K over E root 2 implies sigma of A is equal to A. Sigma of alpha is equal to alpha. Meaning every element of this group maps alpha to itself. So that is the collection we are talking about here. And what is this? This is actually the elements of K not moved by any element from here, that will be E root. Because in here root 2 is not moved, root 3 and root 6 are moved. Of course F is already fixed. So I am going to map. See, I want to define a map from the collection of extensions to collection of subgroups. The way I am going to map is lambda of a general element, we will write it as E, is equal to the subgroup of G over K, sorry, K over F, G of K over F, that fixes E. See, this is the one which this is the subgroup which fixes E root 2. So E root 2 should go against this. So what I am going to write here, I am not going to write the details how we are getting this, but all I am going to say is then there exists a map lambda from the collection of extensions of F to the subgroup of G of K over F satisfying the following properties. And the first property I am going to write is lambda of E is equal to G of K over. And this is going to be G of K over. That is this. See, this is actually the group which fixes E root. So the second property is straightforward. K of G over K over E is equal to E. Or we will write it as E is equal to the fixed field of G K over E. And that is equal to K of, this is actually lambda. Now we have some more properties to go in, and that is the theorem. So I'm going to take this out. So what are the subgroups of G of K over F? Any of this. So let us take one of them. G of K over E root 2. Let us to generalize, we'll say this is an H. It's a subgroup of G of K over F. Now consider K of H. K of H is what? This is here, it's going to be E2. So lambda of K of H is equal to lambda of E2, and that is going to be H, because H is this. See, what you are trying to say is lambda of E root 2 is equal to G of K over, this is our definition of lambda E2. This is our definition. But this I am going to write it as K over this I am going to write it as K over group of K E2, and that is equal to the same thing, G of K over E root. So what I am going to state here is, for any H, subgroup H of G of K over F, here H is this. Then we'll say lambda of, we'll write it here instead, lambda of K, the fixed field of K over H is equal to H. These are all actually the same thing stated in a different way. Once you get hold of one of this, then these two results will follow. The next one is let us take the index of E root 2 over F. This is equal to the left coset of G of K over E root 2 in G of K over F. In this case it is little different, because E root 2 is a finite normal extension of F, which doesn't need to be same all the time, which doesn't need to be a finite normal extension. In our previous example, in the previous result, we said K is a finite normal extension of F and E is in between F and K. Then the last statement of that result is sigma tau belongs to G of K over F, meaning they are automorphism on K, leaving F fixed, induces same isomorphism on E if and only if they belong to the same left coset of G of K over E in G of K over F. The reason behind this one is the isomorphism behind this. We don't know whether E is a splitting field of F. If E is a splitting field of F, this isomorphism will become automorphism, and that is what is happening here. But still we are not assuming that. This is an example, but in this theorem we never said that E is a splitting field of F. So we have to assume that it is not a splitting field. Here it is splitting field, and that is why I am saying the left coset of this. Otherwise it will become the quotient group. We will come there in the next statement. So here so what you will do is, instead of writing this one, you will say the number of left coset of lambda of E root 2, because lambda of E root 2 is nothing but in G of K over F. And the index of K over E root 2 that is nothing but, see, the K of, this is actually a finite normal extension, in which case the index will become the order of the Galois group, meaning this is order of G of K over E root, and that is equal to lambda of K over E root. So we are going to combine these two into next step. So I am going to write this one first, then here. So K over E, this is a general element. The index of K over E is equal to lambda of, or sorry, this is actually lambda of E2, E root 2. Lambda of E, the order of lambda of E. Lambda goes from the collection of extensions to the subgroup. So this is a subgroup of G over F and its order. And we'll write that this one also. E over F is equal to the number of left cosets of G over actually cosets of lambda of E in G of K over F. So the fifth one is one step further than this. Here we are assuming that E is not necessarily a finite normal extension of F. But if it's a finite normal extension of F, so if E is finite normal extension of F, then what will happen? Then G of E over F is isomorphic to G of K over F, the quotient group G of K over. And the last one is, there is one more thing which we don't need to write it, but we'll write that one also. So we'll that is actually the last one is number 6. The extension diagram is similar to the inverted diagram of subgroups. What I'm trying to say here is, when you map lambda goes to K goes to this and F goes to this. But if you look at the diagram here, the smallest field is at the bottom, and these are all extensions of F, and this is the largest extension of in the F in this diagram. Whereas if you take here, this is the trivial subgroup, only one element. It's the smallest subgroup of G over F. And the whole subgroup is coming here. So it's actually inverted diagram. This goes bottom to up, this goes top to down. And that is the last result. So the whole, this is the Galois theory. The 6 items. In fact, if you get one of these, all this follows from the previous result. So we'll do a proof in the next class, but I just want to make sure that the theorem is stated clearly.